So in this video, we're going to be doing motion of a particle and how we can use this formula to define the velocity and acceleration just by using a position function. So what this means is we have some value s, and s is our position, and that one is in centimeters. And our t is our time, and it is in seconds. And so when we take the derivative of this, our ds dt, we're going to be end up with centimeters per second. So let's move this off to the side. We now have our units of everything. So what this means is if you plug in some value of time in here, it tells us where it is located, the particle. So if we plug in 1 second, it'll tell us its location at 1 second. You plug in 0, it's its location. So it looks like this. If I were to plug in 0, it's located at 4 centimeters. And if I were to plug in 1, it's now located at 3 centimeters. So it went from 4 to 3, it went back 3. And so the position of our function is given that way. You plug in a time, and it tells you its location. So the x-coordinate is what you want to look at here for our location. So it looks like this. If I push play, it goes to the right, it goes back to the left, stops, and then goes to the right forever. So it's nice. It gives us everything. You can actually see, because as time changes, you shorten the time, right? You speed it up by that same amount of distance traveled. So the function looks like this. And so relation-wise, at 0, you can see it's 4. And so we're at 4 centimeters. And then it's going to go up. It's going to go to the right. You can see it went from 4 to 4.481 in 1/3 of a second. And so looking at it, you can see it goes to the right. And then it's going to go from 4.481 back to -5. So from 1/3 of a second to 3 seconds, it's going to go backwards. See, back to -5. And then you can see from there, it just goes off to infinity. All the heights are given in infinity. So at 4.55 seconds, we're going to be at 8.33. So if you increase the distance per unit of time or shorten the time for that same distance, you're going to be speeding it up. And that's why we get this kind of a motion, how it looks like it speeds up, slows down to 0, and then speeds back up just by changing how the two are related, distance and time, because that is our derivative. So if we take the derivative of s prime of s, that is going to give us our velocity with respect to t. That is our ds dt. So we end up with 3t squared minus 10t plus 3. And so now we know our velocity, and this is going to be in centimeters per second because we know our units. So what is the velocity at 2 seconds? So if we plug in 2, it will tell us our velocity. So 3 times 4 minus 20 plus 3 is -5. And we want to put units on there. And so the negative tells us that we will be going to the left because it is negative. So our distance is decreasing. So let's look at that. So if we go to 2 seconds, by taking the derivative, we now know that this particle is located at -2, and its velocity at that point, so if you put a little a radar detector right on it, it would pop back saying it's doing 5 centimeters per second, and we know it's going to go to the left. So if I push play, you see it goes to the left. So at 2 seconds, it will go to the left at 5 centimeters per second. So now my question is, when is it at rest? Well, if something's at rest, that means it's going from a negative to a positive, or from a positive to a negative. And the only number you can go through is 0. That's when it's at rest. Its velocity is equal to 0. So if we take our velocity function, set it equal to 0, we now know when it's at rest. So we need to factor this. And we would end up with t equals 1/3 and t equals 3. Now if you remember, if it's 0, this means we have a horizontal tangent. So if we look at our function right there, you can see it's 1/3, and right there it's 3. So those were the two numbers we got, 1/3 and 3. Those are our horizontal tangents, and so what that means is that 1/3 our object stops. So you can actually see it goes, stops, now it's going in a negative direction, stops, and then goes off to infinity. So at 1/3 second it stops, at 3 seconds it stops, and then it goes to infinity. So how this becomes useful is we now know when it's moving forward and backwards. See? Because look, we went positive, stop. Now we're going negative, stop, and then positive for the rest. So we know that it's either moving forward or backward in between those rest stops. So if you plug in a number that is in between these two, whatever it comes out, that is the motion that that object is moving. So if I plug in any number between 1/3 and 3, it's either they're all going to either be positive or they're all going to be negative, because I'm either using right or left. If we're going to cheat, we know. So if we look at it, it goes right, that's positive. It's going back, now it's negative. And then it's going to the right, which is positive. So we already know what we're going to get. We're going to get positive, negative, positive. But we got to do this algebraically. So we plug in some numbers that are within that region. So we know 0 is our starting point because time starts at 0. So v prime of 0 and between 0 and 1/3. So if I plug in 0 into our velocity, and I like to use the factored form because they tell us everything. So if I plug in 0, I get 3 times 0, which is -1, 0 minus 3, which is -3, and that's a positive. We don't even care what the number is. It's positive, which means we're moving forward, and that matches. And now the next one we knew was going to go back, so let's use red. In fact, I'll just change that to red because we know it's going to come out negative, which means we're moving backwards. That was our picture. So if I plug that in, plugging in 1, we get positive. We get +2. Plugging in 1, we get -2. And a positive times a negative is negative. And then the last one we plug in is 10. So that's 30 minus 1 is 29. And 10 minus 3 is 7. Both are positive, so multiplying gets positive. So we're moving right. So when is the particle moving forward? It's going forward from 0 to 1/3, and then also from 3 to infinity. And it's going backwards from 1/3, and I'm putting parentheses here because at those more other at 1/3 and at 3 they are at stopped. It is 0, not positive or negative. And there you have it. So now we can figure out the main question is, what's the total distance? Because think about it. If someone watched you walk to school and then walk home, you're just going to be a total distance of 0. But that's not true. You walked to school, which means you walked, say, a mile. And then you had to walk home, and so you walked another mile. But you could have walked from your house to the school, to the restaurant to get some food, and then you walked back to school, and then back home. Each of those locations is where you stopped. And so we want to find all the places that you stopped, measure the distances traveled between each one, and then that gives us our actual total distance. Otherwise, you're going to be looking at 0. So we know from 0 to 1/3, we stopped. And then from 1/3 to 3, we then stopped. And then from 3 to 5, we stopped. And then from 0 to 1/3, that was positive. That one was negative. That one was positive. And so our directions look like this. So now we know our motion. So we know from 0 seconds to 1/3 seconds, we were going to the right. And then from that 1/3 seconds to 3 seconds, we were going to the left. And then from that 3 seconds on, we're going to the right. And so what we want to do is find out what was that distance, what was that distance, and what was that distance. So if we use 0 and 1/3 and we plug it into our position function, it'll tell us where we're located. So what we're going to find is s of 0 minus s of 1/3. And it doesn't matter the order here. You're going to take the absolute value to find the distance. And then we're going to do it again. S of 1/3 minus s of 3, absolute value. And then position at 3 minus position at 5, absolute value. And that will give us our distance traveled. So we need to find s of 0, s of 1/3, s of 3, and s of 5. So a quick way to do that is if you take your TI calculator and you plug the function in, so x to the power of 3 minus 5x squared plus 3x plus 4. We plug this in, and then we go to our window, and we plug in our units. So we're going to be going from 0 to 5. So come on, window. So our x-min is 0. Our x-max is 5. Anytime you know your region, you want to plug it in. So that is our domain for this problem. And then you hit zoom fit, which is 0. And it'll graph our picture in between that. So you can see we went to the right and then to the left. So we increased, decreased, and then increased. That's our 1/3 and our 5. So if we hit trace and 0, it tells us our number. So it's 4. So s sub 0 is 4 minus, in fact, I'm just going to put the parentheses here. Put the minus in there. And we just do that for each one. So now if you hit trace and then 1/3, it says it's 4.4815. So move it over now, 4.4815. So I should probably just erase this. And then we do it again. So s of 3, so trace 3 is -5. That's what we knew. So 4.4815 minus -5. Make sure you put that in parentheses because it's going to be a plus. See, what's happening here is we went from here to here, and so that's a total distance of 9.481. So we want to make sure that we do a subtraction of the two. Okay, and then now we just need one more, and that's s of 5. So trace 5. 19. Okay, so down here we want to change that arrow, and we know we're stopping at 5 because it's at 5 seconds. So now we can find all of these distances. So this would be 0.4815, a very small distance traveled. This is 9.4815, and this is 24. So again, just to give you a picture, from 0 to 1/3, we're now here. So from 0 to 1/3, that was our distance. And then we went from 1/3 to 3. So that was our second distance. And then from 3 to 5. So you can see that 24 and the 5 together give us, sorry, the 19 and the 5 together give us 24. So if we add all of these up, that is our total distance. So that's 33.963. And again, it's centimeters because each of these is S. These are S, so it's centimeters. That's how far we've traveled. So picture-wise, that would be 0.4815 centimeters that way. And then we did the particle did 4815 centimeters to the left. And then it did 24 centimeters to the right. And so that is its total distance. That's why we need to find out when it stops. Okay. Now the next question is find the acceleration here at time t. So acceleration is the change in velocity. So if we take the derivative of our velocity, it tells us how our velocity is changing. That's acceleration. So if you went from, again, say 10 miles per hour to 15 miles per hour in 1 hour, then that would be a 5 mile per hour change per hour. That's acceleration. You accelerated from 10 to 5. Okay, so we're going to take the derivative of the velocity with respect to time, and that would give us our acceleration with respect to time. Let's go back up. There's our velocity. So it's 6t minus 10. And now we want to write units. So dv dt. We know our velocity is centimeters per second. And then we added another time. So we end up with centimeters per second per second. So it's the velocity per second. But we can also just write it as centimeters per second squared. So that is our velocity. So what's the acceleration at 2 seconds? So if we plug in 2, this would be 2 centimeters per second squared. So what that means is the velocity is going to increase by 2 centimeters per second at 2, which means it's accelerating. Correct? Maybe not. So what we need to do is know if it's accelerating or not. So if you think about it this way, if it's moving in a negative direction, like negative 5, and our acceleration is actually 2, then what it's actually doing is slowing down. So if you look at our problem, at 2 seconds, its velocity was negative, so it's moving to the left. But our acceleration means it's moving to the right. So even though it says 2 centimeters per second squared for acceleration, our particle is actually slowing down. It's decreasing, because what's negative 5 plus 2? It's 3. So we're getting an approximate that it'll be 3 centimeters per second 1 second later. All right, so what we have to do is look at the signs. If you look at the signs for each one, then it'll tell you where everything is. Sorry, that was a 3. And so we're going to trace everything we had. That was positive, negative, positive. I want to put that in red. And if we do another table next to this one, so when does the acceleration become 0? So when does it stop accelerating? When did it hit its final part? So we do the same thing. So 6t minus 10 equals 0. 6t equals 10. Divide by 6. Divide by 6. T equals 5 over 3. So at 5/3 seconds, our acceleration is 0. And what that means is it's going to change from a negative to a positive, or a positive to a negative. That's what it means. So we need to plug in a number over here. So acceleration at 0, and then acceleration at 2. We've already done that. It's already up here. At 2, we got a positive. Let's put it up here, positive. And so what did we get for 0? So if I were to plug in 0 into this function, so a of 0 would be 6 times 0 minus 10. It comes out negative. So that means our acceleration is negative from 0 to 5/3, and it is positive from 5/3 on. So when is it speeding up? Speeding up means they have the same sign. So it would be either this direction. Oops. Let's do the red. It would mean that we are doing a negative velocity, and our acceleration would also be negative, so there they are going the same direction. So if we had like negative 5 and negative 2, we would be getting a negative 7 1 second later. Here, let's write this. Centimeters per second. Centimeters per second squared. So this would become negative 7 centimeters per second 1 second later. And if they were both going this way, that would be like 5 centimeters per second and 2 centimeters per second, both positive. And so now we would end up with 7 centimeters per second 1 second later. But if one is doing positive and the other is negative, then when you add them together, you end up with 3 centimeters per second 1 second later. So what that means is that it slowed down. So if the signs are opposite, that's deceleration. So we're going to mark these with pink for decelerating. So from here to here, this is decelerating. Where else are the signs different? Here. You can see that they are different signs. And then we're going to do a light blue for good. So this is accelerating. You can see they are both negative in this region. So between 1/3 and 3, it's negative. and between 0 and 5/3 is negative. So that's an acceleration. And then at the very end, it's a positive. So now we just use those numbers between the velocity and the acceleration to tell us where. So speeding up. That would be between 0 and 1/3. Oops, speeding up is the blue. So between 1/3 and 5/3, union 3 to infinity. Slowing down, that would be between 0 and 1/3, union 5/3 to 3. And then these should make sense to you as well, because just think about what's going on. So from 0 to 1/3, it's slowing down. Why do you think it's slowing down? Well, let's look at our velocity up here. What is it doing at 1/3? It's stopping. So what do you have to do before you get to 1/3? You have to slow down. It has to slow down to get its velocity down. So right now we have a positive velocity, but we need to slow down to stop. And then it's going to speed up, but then it's going to do what? Slow down and stop. So right here is stop, and right here is stop. And so what's happening right before stop? It's slowing down, which makes sense. So let's look at our picture. So you can see it's, see, watch, sorry. Slowing down, speeding up, slowing down and stopping, and then it speeds up from there on out. So that's what happened. It slowed down and stopped, sped up, and then slowed down and stopped, and then sped up. It's just like you. These are stoplights. And so you're stopping, slowing down to stop, speeding up, slowing down to stop, and then speeding up. Everything works perfectly. And there you have it. That's all of the questions in one. I know this is a long video. Hopefully you can fast forward through some of it, but I wanted to give you everything in one problem. Thank you.